All right. Every slide has audio, so if you ever see a slide and you can't hear anything, let me know through text or through voice so I know that it's not working. I have a new monitor that I have off to the side, so I'm now able to see the incoming chats and my PowerPoint off to the second monitor, so that's very nice. So we're going to talk about units 35, 36, 37, 38, 39, basically the next 8 units. Sculpting and weathering, mass movements, water flows, and so on in different kinds of environments related to erosion and weathering. This picture here is of Goblin State Park in Utah. Basically, these are sandstone pillars that have been sculpted by wind erosion for the most part. And southern Utah has lots of amazing national parks and state parks. It's an impressive spot to visit. Here are some more pillars of stone that are in Goblin Valley, Utah, sculpted again by weathering and erosion. So processes shaping landforms and landscapes. A landform is a specific feature that is discrete and can be studied on its own, like a lake or mountain, and a series of landforms make up a landscape. In this particular picture, one mountain would be considered a landform. The aggregate of mountains would be considered a landscape. Sometimes when you're talking about a broad region, landform is used to refer to any major geographic features of that region. So if you're talking about the US, you might say the Great Lakes are a landform or the Rocky Mountains are a landform. But specifically, a landform is one specific discrete geographic feature that can be studied, and numerous landforms make up a landscape of mountains or prairies or so on. So this here is in the Rocky Mountains, Colorado. These were sculpted by erosion and volcanoes and lava and glaciers. So many different things have sculpted the Rocky Mountains over millions of years. So processes that shape landforms and landscapes. Weathering is the breaking down of rocks in their place. When it's moved away from where the weathering took place, that's called erosion. And weathering can be breaking down using a chemical, mechanical, or biological process. Mechanical process is something that physically beats down on the rocks, such as rain or snow. Chemical is a chemical reaction, such as oxidation or rusting. And then biological is something like animals or plants, tree roots breaking up the ground, or tunneling rodents. Tunneling landforms are an example of biological landform changes and erosions. So mass movement is a gravity-driven downslope movement of Earth's material. There are different kinds of mass movements: landslides, avalanches, mudslides, and so on. This particular picture here is a mudslide that came down on a bike path near Sacramento in 1985. When you have heavier rain, you're more likely to have mudslides and other kinds of mass movements and landforms and so on. Lately, California has had a lot of landslides because they've had very heavy rain from atmospheric rivers that have hit over the last 4 to 6 months. And those were very useful because they help alleviate the drought they've been going through for about 6 to 7 years. But now they have too much water, at least at the moment. Lots of landslides are and fancy people on hills like this are starting to lose their homes as erosion is causing more landslides near homes. So the process that shapes landforms and landscapes is often running water. That's the most effective agent of erosion. Running water mixed with gravity that makes the water move. So particles transported or modified after they're subject to erosion, water particles and sand particles and so on, when they move downriver, they often are broken up into smaller parts and they're often smoothed and sanded down. So if you see a rock that's smooth, it's usually been weathered by some water of some kind. And rivers are a very important part in shaping the landscapes of different places around the earth. We'll talk about the Mississippi River. Pictured here is the Yangtze River in China, and it has very dramatic and beautiful landforms along the Yangtze River. It's considered a very pretty river. It runs through much of the central part of eastern China. It's a very long river, kind of like the Mississippi, and it has lots of industry and large cities on it. Shanghai is near where the Yangtze River meets up with the Pacific. So it's a beautiful and important river in Chinese culture, like the Mississippi would be here. So rivers can be used for carving rock and creating valleys and floodplains and other things like that. So glaciers are also very important. Glaciers covered much of the Midwest about 20,000 years ago. The last glaciers were treated roughly 15 to 20,000 years ago, and they can carve valleys and they can make real dramatic change to the landscape. This here is a valley in Yosemite National Park, the Yosemite Valley, and on the left here is El Capitan, the large boulder, the large cliff you see on the left here, and that's a large granite monolith. Here is El Capitan in more detail. It's about 3,000 feet high. It's one of the most important, impressive features of that park. And there's actually a guy named Alex Honlode who climbed El Capitan freestyle, no ropes of any kind, no ropes or straps or anything. He just crawled up it. He spent years preparing for it. And there's a real interesting documentary called Free Solo that follows Alex as he climbed this rock. He had some friends follow him along who were wearing protection ropes and so on. And they filmed him the whole way and made this documentary. So that's really interesting. He did it in about 3.5 to 4 hours. And it's an amazing documentary worth seeing. So wind also can change landscapes in addition to glaciers and rivers and so on. Wind is a relatively minor agent, but it can be important for shaping landscapes over time. Wind can shift dunes around. It can blow sand above one side of a dune on the windward side, then the leeward side is out of the wind. And then over time, this can actually shift the dunes. This is the Nambian Desert, and this is a result of wind erosion of nearby mountains. So the mountains basically erode, that turns into small sand pellets that focus and move into the valleys, and then those are further moved around by wind. Coastal processes can also shape landscapes. Waves along coastlines can break down rock formations and cause beaches to develop and so on. This particular picture is along Route 1 in Oregon's coast. It displays natural bridges that have formed from wave action or wave erosion. Occasionally, those natural bridges can kind of collapse, and then you might have a pillar or a spot where a bridge used to be. This is interesting because this part of Oregon is a CSB climate, which is actually a cool summer Mediterranean climate, which is relatively rare. So they have dry summers and they have cool, wet winters, but unlike, say, Athens or Rome or LA, this is a little bit cooler. So it's that kind of climate, but with a cool summer and then rainy winter. So it's a unique climate. CSB climates are fairly rare. Here's another picture of the Oregon coast. And again, a lot of it is really beautiful along the Pacific Ocean. Those rock formations you see are called sea stacks. And basically those are rock formations that have eroded around them, but are made out of harder rock. So those sea stacks are still there. And when you have a lot of erosion along rivers and so on, a lot of the sand is deposited along the shore or formed by rocks that are near the shore that are broken down by the ocean. And then you can have large beaches form. This is the Louisiana Gulf Coast. And the sand there was deposited by sand dropping it off on the ocean during the tide, or if you're near the delta of a river, sand and mud can be deposited by rivers that are carrying sediment in them. So dunes, beaches, deltas, and so on are formed with depositional landforms. That means material that is deposited by oceans or by rivers or so on. So gravity is another important element. Water needs gravity in order to have it move. So where you have steep relief, where you have a change in elevation, you have faster moving water and you have more erosion caused by gravity. So hillside rocks and streams and glaciers move downslope with gravity-driven water. And again, where you have steeper slopes, you have faster moving water and more erosion along those areas. This is erosion along California's coast due to waves. So this is interesting. This is a house on Lake Michigan, actually. Lake Michigan is slowly eroding like it is along the Pacific in California. And there are many homes along Lake Michigan that have fallen into Lake Michigan due to erosion, due to waves from Lake Michigan wearing down the sand. It's partly natural. It just happens over time. This particular homeowner built a formation of rocks to try to fortify his property. And it must be working because his neighbors, you can see the waves are pushing back the sand, but where he fortified it with rocks to create a break, his home is at least temporarily protected. So you can fight against erosion to some degree by creating kind of barriers and blocks and so on to prevent erosion. So tectonic uplift and tectonic motions are also important when you're creating landscapes. Land can be pushed up for reasons we've studied in the past. So you can have mountains that are simultaneously being eroded because of water and also being pushed up because of tectonic uplift. The Himalayas are still rapidly growing. The Appalachian Mountains are slowing down. They're not growing as much as they were at one point. But as they erode, they become lighter, and then you have the isostatic rebound that we talked about, where it actually gets pushed up by the mantle underneath the Earth's crust, and as it becomes lighter, it's pushed up. So many mountain ranges are simultaneously being pushed up and being worn down with erosion at the same time. So this is Mount Rainier in the Appalachian Mountains. And this particular picture here is the Wind River Range in Wyoming, and that has been lowered by erosion. Here's a little more information on the Wind River Range. That is Fremont Peak. It's the third highest peak in Wyoming at 13,751 feet. So some weathering processes. This is a picture of Salvador, Brazil. This is a wealthy city in Brazil that was very wealthy in the early 1800s from whaling and also from plantation agriculture. Lots of sugarcane and tobacco was being grown in the area. So they have lots of homes for the 17 and 1800s. Then it lost a lot of wealth in the late 1800s and fell into disrepair. And then some of the buildings were restored starting in the 1990s, and now it's kind of a major tourist attraction. This is a picture of one of the main roads there. So part of it has been restored, but where you have cities near the ocean, and this is true in Charleston, South Carolina too, you often have salty air and storms, and that can wear down buildings. So they need constant maintenance where they can be worn down and weathered by erosion. So weathering impacts elements. Basically, this particular picture here is an example of a rock, and those little holes you see there are subject to collecting water, and then that water can cause chemical erosions or chemical changes that can make the little pit even a little bit deeper. So sometimes in rocks, you'll see these little water pits that collect rain and then increase the erosion process. So again, types of weathering are mechanical, biological, and chemical. This is an example of mechanical weathering, also known as physical weathering. That boulder you see was actually previously surrounded by softer rock and softer materials. And then while it was covered, it was broken down and eroded with water. And then the lighter materials around it wore away. And then this large block of igneous rock, which was harder, remained. So sometimes when you see a large curved rock, it was previously covered by other rocks, and then those wore away to expose the large curved rock. Other kinds of physical weathering are frost action. That's where you have, frost, water seeps into a small crack, then freezes and then pushes it open. Salt wedging is when salt in deserts and usually coastal areas can get into small cracks and then crystals can form, and that can kind of push and break open the rock. And then exfoliation is sheets of rock that form after overburden pressure is removed. You might have heard the phrase exfoliate when you're washing your face. A lot of ads talk about using soap to exfoliate your face. It's kind of washing away the dead skin, and the same idea is true with rocks as well. It kind of push or brush away an outer layer of rock or dirt to expose the rock beneath it. This is a rock field where you have large rocks. Sometimes they'll roll down the hill and they'll collect at the bottom of the hill. So this is a particular example of a block field that's in Colorado. Sometimes these are called rock seas or Fleisenmeers in German. And basically they're where large piles of rocks that have pushed downhill due to erosion and gravity collect in large areas here. An example of the frost cycle in Michigan is our roads. We have fairly bad roads here. Part of the reason is we have a temperature where it hovers right around freezing for a lot of the year. If it was a lot colder or warmer, it wouldn't be as much of a problem. But as you know, from the last 5 months, it's common to have it just above freezing, and then water or drizzle rains down and gets into cracks in the street. The nighttime comes, it gets below freezing. Those little cracks filled with water, they expand when they're ice, and then that can break down the roads just like it can with rocks, and that's caused the frost thaw cycle is a menace for roads as well as it is for rocks, and Michigan's kind of notorious for it. Chemical weathering is an alteration in minerals. Unlike mechanical weathering, which is physical, chemical weathering is when there's a chemical change in a mineral. Again, rusting might be a good example of that. Water is essential to have chemical weathering, and different types of chemical weathering can lead to these spheroid-shaped boulders. They look somewhat like the boulders we saw that were created by mechanical weathering, but this is the same thing that's happened with chemical weathering instead of mechanical weathering. So sometimes chemical weathering can lead to these sphere-shaped boulders as well that are exposed when the softer land around them gets worn away. So some of the chemical weathering processes is carbonation. That is when carbon dioxide gases dissolve when water is mixed with it. This is common in some karst regions, which we'll talk about in a little bit. And this also is common in limestone and dolomite. And what can happen is vegetation can increase the acidity of water that can then seep into these rock formations. And then acidic water can lead to a faster chemical reaction that can increase the carbonation process. Other chemical weathering processes, hydrolysis and oxidation. Oxidation is basically rusting, and this is common in iron-bearing silicates. So where you have iron that reacts with water in the air and oxygen and can create rust. Rust is not always bad, though. It actually can be a positive thing. This is the Statue of Liberty. When it was originally given to us by France in the 1800s, it actually was gold on the outside. And then what happened, and this was known that this would happen, is the iron, which originally was gold and traces of copper, rusted and turned into this kind of light green color. And this is oxidation, but this actually helps protect the Statue of Liberty from further erosion. So the thin layer of rust caused by oxidation actually protects the Statue of Liberty from further rust and erosion. So rust actually can be beneficial if it's done in a way that can protect metals. In biological weathering, this is an example of rock and sand that's being worn down by trees or roots or burrowing animals or things like that. Holes in the ground can be dug by groundhogs or even some birds. And where you have roots or burrowing animals, it increases oxygen and water that gets further into the rock and the sand, and that further increases the weathering process. So we talked a little about frost wedging and salt wedging and so on. These are more examples of spheroidal mechanical weathering granite boulders that are in Wyoming. Granite can weather in all climates. Limestone is relatively resistant to weathering unless water is involved, and then it's subject and vulnerable to chemical weathering. It's relatively immune in dry climates where you'd have more physical weathering, but limestone is vulnerable to chemical weathering and chemical reactions that way. Here's another, this is called a woolstack weathering in England, and this is another example of rocks that have been eroded and worn down with chemical and physical weathering, and then the softer rock around them was worn away, leaving the harder rock exposed. So this is in England. So mass movements is when you have a sudden gravity-inspired movement of land, downhill movements of earth material forced by gravity, sometimes rapidly, sometimes slowly. They could be mudslides, avalanches, rock slides, and so on. This particular picture is in Peru, and this is a rock slide that happened in the 1970s. They can be dangerous. This particular rock slide moved 11 miles at a maximum speed of 270 miles an hour, it's estimated. So this rock slide happened incredibly fast. Again, 270 miles an hour is faster than any race car, and 25,000 people died when this rock slide happened suddenly. People often live in river valleys or mountain valleys because it's often very rich soil and relatively flat. If you're in a mountain range, you would want to move to where there's relatively flat land and rich soil, but those areas can also be vulnerable to rock slides and avalanches. So you have a mass movement of material when you have a slope failure. And basically that is when you have gravity continuously pulls down on rocks and dirt and so on and hills. And you have some gravity that's pulling an object into the slope that it's on and some that's pulling it down. And where you have something that doesn't move, that's because there's enough friction or cohesion to prevent it from slipping. Friction is kind of like traction. And then where you have something that starts to slip, that can cause a rapid downward movement of rocks or other kind of materials. So cohesion is the tendency of slope materials. And frictional strength is the resistance to downhill motion. So when you have something move downhill, that's called slope failure. Certain kinds of material are more resistant to slope failure. Loose sand will start sliding down if it's tipped up to about 33 to 35 degrees. Some materials will tip sooner than that, some will tip later than that. So The angle of repose is the steeped angle at which a given slope material will remain stable and not fail. So that's as steep as something can get before it starts to slide is called the angle of repose. Water pressure is important when it comes to mudslides and so on. If a slope becomes saturated with water, it loses friction and you're more likely to have mudslides or things of that nature. This is a debris slope in the Sichuan province of China triggered by heavy monsoon rains. So water can fill pores and then it just makes a slope more slippery and more likely to have a slope failure. Some slope failures are slow. Mass wasting is basically kind of a very slow-moving slope failure. A good example of that would be a creep. A creep is a slow, almost imperceptible mass movement. This particular diagram kind of shows poles being tilted and graveyards being tilted over and so on. This often happens where you have freezing grounds that freeze and thaw. You often will have creep. And another example of creep is here. This is a forest, I believe, in the Appalachian Mountains. And you can see the trees are tilted and then they kind of bend upward. And that's because this ground is slowly moving down, but the trees are having enough time to adjust by continuously turning and growing upward towards the sun where they want to be. So this is an example of how vegetation can adapt to a slow-moving creep. So mass wasting. This is when you have lots of material kind of sliding down in the form of an avalanche or a slide. There are two forms of mass wasting, and that is a slide where you have kind of a straight angle and you have rocks or debris coming down at a straight angle. And then you have a slump, which is the same idea, but it's on a curved plane instead. So on the right here, you can see there are different layers of clay and other sediments, and then the slump happens on a curved plane while the slide happens on a straight plane. So it's kind of easy to remember. If you go down a slide at a playground, those are usually straight, and then the slump has a curve or a slump in it. In addition to mud and solid materials, you can also have kind of loose materials that can degrade in the form of mass wasting. Fluid movement of loose earth can be broken down into earth flows or debris flows or mud flows, kind of like what we talked about before, but with material that's looser and not as solid as before. And where you have these loose materials, you often have kind of a lobe where it started to fall from, as you see in this diagram here. A rock fall is another example of this kind of formation. And this is a rock fall that happened in Afghanistan. I'd hate to have to get that out of the way. That would ruin your commute. But Afghanistan has lots of mountains. It's an area that can be vulnerable to occasional quakes. And this is an example of a massive boulder rolling down into the middle of a road. So where you have large amounts of small rocks form, sometimes the small rocks and stones can form cone-shaped areas at the bottom of where it's deposited called talus. This is a talus cone in Banff National Park in Canada. And it's kind of an example of where lots of small little particles pile up into one triangle-shaped area. So different parts of the U.S. are vulnerable to landslide risks. Michigan is fairly vulnerable along Lake Michigan, as we've seen in some other pictures. Lots of beautiful dunes there, but dunes are not real solid. And if you build on dunes, you can take away some of the vegetation that anchors it down. That's why you often will see dunes eroding when they have homes built up against the dunes. So it's something to be concerned about. And another home in Lake Michigan sliding into the lake. This person didn't have that large rock barrier that the previous person did. So water is an important part of erosion, and this Unit 838 is about water in the lithosphere. Of course, the lithosphere is the outermost rocky part of the Earth's 5 main spheres. And water can come down in the form of rain or snow, and then it gets into the rock and the soil and significantly influences it. This particular picture is groundwater heated by magma in Yellowstone National Park. And the weird chemicals and beautiful hues you see are different bacteria that can live in the hyper hot water that give off unusual colors. Here's another picture of a geyser in Yellowstone. This is the Grand Prismatic Spring in Yellowstone, the 3rd largest hot spring in the world and the largest hot spring in the United States. So Yellowstone National Park is really amazing. If you have a chance, I suggest you go out there and visit it if possible. So when you have water that comes down, not all the water coming down actually gets into the soil. Some of it is captured or intercepted by vegetation in trees. Uh, Pine forests actually capture a lot of the rain that comes down. You think thin needles wouldn't be good at catching rain, but in pine forests, like you have in boreal forests, about 40% of the rain that comes down is captured by these needles in these forests, and they never actually get to the ground. They land on the needles and then they evaporate back into the atmosphere. The 60% that do get to the ground are then often absorbed into the ground, and that's considered infiltrating the ground or being sucked into the permeable ground. And then some are blocked by impermeable surfaces. An impermeable surface is anything where the water does not flow into it. Urban areas have a lot of impermeable surfaces, roofs, parking lots, and so on. So some of the water lands on vegetation and evaporates. Some of it's sucked into the ground, and some of it lands on top of the ground, but it's not sucked in, and it basically becomes runoff. So different kinds of surfaces have different kinds of infiltration rates. More vegetation usually will absorb more water. This picture shows a meadow versus a cornfield, and a meadow will absorb more water than a cornfield will. And if rain comes down relatively slowly and steadily, more of that water is likely to be absorbed into the ground. If it comes down real hard and fast, the water might get saturated with water, and then you'd have runoff, or it might not even have time to get absorbed into the water, and it might just form runoff, where you have water that's not absorbed into the ground. It goes into a creek and then a river and then possibly out to the ocean. So slow and steady rain is more likely to be absorbed into the soil than heavy, fast rain, and more vegetation usually leads to more water being captured in the soil. So water flow in streams, where you have steep relief, as we've talked about, you have faster moving water and generally more erosion. The gradient of a stream is basically the slope of a stream. You measure how long a stream is over a certain period, how much of a change there is in elevation, and then that's the slope or the gradient. With streams, it's a little different than with, say, a pipe, because streams, of course, zig and zag. They're not a perfectly straight line. But this is how you would calculate the gradient, as you see there. It's basically just change in elevation plus length, and then you divide the change in elevation by the length in order to get the slope of the gradient. This is an example of very sharp gradient. This is Tequamanon Falls in northern Michigan, the Upper Peninsula. It's beautiful. If you haven't a chance, I suggest you go there. This is the Upper Falls. There's another part of the falls about 4 miles downriver that's equally pretty, but not quite as dramatic. These falls are 48 feet tall. About 7,000 gallons of water per second move over the falls. And it's got a brownish hue because of tannins in the water. Tannins are naturally occurring chemicals that are formed with vegetation and give it kind of a reddish brownish hue. The Amazon River actually has a lot of tannins in it as well, and it has kind of a brownish hue to it. It almost looks like tea. So where you have flowing water, this is a diagram of a channel or a river. The top one is looking at a channel or river from the side. You typically have the strongest movement and strongest speed of water just below the surface of the water. And also the center of a stream, if it's a straight stream, will also have the strongest current. So different parts of the river move more slowly or more quickly. Near the surface is faster, and in the center of the stream is generally faster as well. And if you have a curving stream, you'll often have one side of the river that is on the inner part of a curve that the water moves slower, and usually you have water and sand depositing sediment there. And then the outer part of the river is usually faster moving, and that's where you tend to have more erosion. And the little red line you see here is the fastest moving part of the stream, usually just below the surface over the deepest part of the stream. And that's called the thalweg. That's what the red line is. And this particular picture kind of shows you cross sections of different parts of the stream. The number 1 on this long river coincides with the number 1 on the diagram on the top. 2, 3, 4, and 5 is on the bottom there. And it kind of shows the river has different shapes depending on where it is on the curve. Where it's relatively straight, you have it relatively even on both sides. Where there's a sharp curve, the inner part is shallower and there's more deposition and more sand being deposited, and the outer part is faster moving with more erosion. So if you like to measure how much water is moving through a river, you can measure the river's discharge, and that's water passing over a cross section of a river at any given time. Usually we think of a river as discharge of where the river ends up, how much water is measured when it goes into the ocean, it goes into a lake. But really, any point you can measure the discharge of a river. And essentially that's the amount of water passing over a certain amount of time. So discharge equals average velocity and the area of a cross section. So how much water is passing over a certain part in a second or a minute or so on. In order to measure this, you have to take numerous different readings in different parts of the river at different elevations and at different points, measuring how fast the water is in order to collect it. They used to have people who would cross over little cables on a little cart and take measurements now. Now it's a little different. It's not quite as exciting. They usually have drones do it now. You just have a little computer and a rope, and then the little raft with the measuring thing sits on top of the river, and you can program it to measure it at different depths and so on. So not as dramatic as the previous picture. Sometimes you can just stand in the water and take measurements while you're standing in waders. So modern technology is not as interesting as it used to be to take water measurements. So where you have rivers, you often don't have a steady flow of water, but it can go up and down depending on the time of year. Right now we've had some rain. There's been lots of snow melt that's starting to hit the west. So many rivers are at or near peak. And this is an example of a hydrograph. Basically, this chart shows how much water is passing a specific point in a river at a given time. This hydrograph shows discharge associated with an individual storm, the St. Mary River in Nova Scotia, Canada, but it could apply to any river. And you can have a big upswing in the amount of water that passes a certain point, and then inevitably when most of the rain leaves, then you have it drop down to more normal levels. But it shows you can have significant swings in how much water passes by a certain point in a river in a certain time or in different times of year. Usually spring is when you have the heaviest amount because of snowfall and rain and so on. So beneath the surface of the earth, water beneath the surface saturates the earth below a certain area called the saturation zone. And then above that, where it's dirt but it's not saturated with water, that's called the vadose zone or aeration zone, because there's air there. It's not completely saturated by water. And the top of the saturated zone is called the water table. So if you were to create a well, you'd want it to drill down until you get to the zone of saturation, and then that's when the well would start to fill up with water. So this particular diagram shows the vadose zone. There isn't land saturated with water, the saturated zone below that, the water table, and the land surface, and so on. So water tables are not necessarily completely level. They tend to curve in along with the land. So if you have hills that go up and down, then the water table would at least partially follow the hills and go up and down as it follows the landscape. There's a little more information on the groundwater in the saturation zone. If you have a large amount of underground water, that's basically an aquifer. And aquifers they can have movement where it goes around an unconfined aquifer, or an aquifer can be sandwiched in between two hard layers of rock, which is considered a confined aquifer. And if you have water that goes down into a confined aquifer, it can create pressure that can push the water up above the water table and even up into the land. So this is an example of an artesian well. A part of France that these wells are named after had lots of confined aquifers. So when they would dig a well, instead of staying there, it would sprout up and go several feet into the air. So that's when you have a confined aquifer. Most aquifers are unconfined aquifers where they just sort of freely move around underneath the water or underneath the earth. So these are examples of artesian wells. The one on the left is in northern Michigan. The one on the right is at Cascades Park or Sparks Park right here in Jackson, Michigan. So Jackson, Michigan has its own artesian well. And other kinds of aquifers are perched aquifer. That's an aquifer where you have a large amount of water kind of perched up on a hill. Sometimes it will leak and go down the side of the hill, as you see in the top left there. And then you can have, again, as we talked about, confined aquifers. If you have an aquifer near heated rock, that can lead to a hot spring, as we saw some pictures of at the beginning of this. And then you can have a spring where you have an aquifer that naturally just seeps up through the ground and dribbles down, not necessarily like an artesian well, but a spring is any place where you naturally would have an aquifer coming up to the surface of the earth. And then you can have a temporary spring where you have a high water table temporarily, and then springs can form and drain into a river, and then it can go away as the weather gets drier. So those are different kinds of water tables. So as you draw water out from below the earth, this can cause an area around where you're drawing the water to become lower, or that's called a cone of depression, and that can actually affect nearby wells. So if one well is pumping a huge amount of water, it can reduce the amount of water at nearby other wells and then bring the water table down. So this is a problem in areas where there's extensive fracking or agriculture. In parts of California in the Imperial Valley, they've been taking underground aquifers and underground waters out of the water for so long that the levels of land have actually sunk sometimes 10 or 20 feet, because when you pull up water, you're pulling up mass, and then the land above it can slowly sink. So where you have too much water being pulled out, it can cause a lot of environmental problems with wells nearby running dry and water slowly sinking because the water below it is being pulled out. You can also have problems if you have a fresh underground water source near a body of salt water. If you pull too much water out too fast, you can start to draw salty or saline water near the water source. And then you either have to pull the salt out with desalinization or look for a new underground water source. So pulling water from underground has to be done very carefully. The good news is, again, as we mentioned, California had this terrible drought. A lot of their reservoirs were very low, but because of the heavy rain they've had from their different rainstorms over the last 5 months. This is a picture of before, about 5 months ago. This is dropping water levels in California before the rains came, and then after. The picture on the right was taken just about 3 weeks ago. So this is a reservoir in California that's been replenished because of the atmospheric rivers that they've had. Humans can also contaminate groundwater as well as pulling out too much water. This is an example of how a factory often will have a waste pool where they spill out any water that's been contaminated with chemicals that they don't want to go into the environment. They're supposed to remain in that waste pool, but sometimes that water can seep into the ground and contaminate water sources nearby. They're supposed to check for this with contamination wells set up to detect contaminated water or contaminated soil. But occasionally you can still have situations where chemicals can leak, especially around natural gas or factories that use PFAS, what's called a forever chemical. These chemicals can, if you're not careful, inevitably leak into the natural environment and drinking water. So any factory has to be monitored very carefully so they don't contaminate nearby water. So Unit 39, slopes and streams. This particular picture here is of the Badlands in South Dakota, and that's mostly sedimentary rock, sandstone. You can see the different layers of sediments that have built up over millions of years. There are a lot of fossils that have been found in the Badlands of South Dakota, and rain and wind erodes the relatively soft rock into these unique landscapes here. Here's another picture of Badlands. Badlands, Lakota people call this place Makosika, which is badland, and they called it that because it's not really great. You can't really farm on it. It's not flat. It's sort of considered wasteland, although now it's very beautiful. But to the native people who lived there, it was land they really couldn't use for anything. They couldn't hunt, couldn't raise food on it, so it was just sort of wasteland or badlands. This area also has huge temperature swings too. South Dakota can go into the low 20s to the high 90s in a relatively short period of time. So erosion caused by water, erosion can come down in the form of rain and cause something called rain splash. And that's when rain comes down, hits the ground, and kicks up tiny little particles of sand and minerals that can then flow down hills, forming tiny little streams of water called rills that can eventually form into larger streams called gullies, as you see on the bottom right there. So rain splash it causes erosion that kind of pushes sediments down slope. Vegetation can impede this. If you have lots of grass or trees, it anchors down the ground and slows down the speed of erosion. So there are lots of rivers in the Midwest especially, and if a river gets water in a certain area, rain will come down and it will usually flow into a nearby river that moves into a larger river that's a tributary of one. And then in the Midwest, much of it eventually leads into the Mississippi River Basin and goes into the Mississippi River and eventually goes out the Gulf of Mexico there. So this green area here is an example of the Mississippi River Basin. Rain that comes down in that green area would eventually work its way into the Mississippi and the Gulf of Mexico. There are other river basins in other parts of the U.S. Michigan is not part of the Mississippi River Basin. It has its own river basins that go out into the Great Lakes. And you can see that little red line there is the Continental Divide. That is basically rain coming down on the east of that flows into the Mississippi River or Colorado River, and on the west would flow into the Pacific. So that little ridge literally divides the continents into water flowing east or water flowing west. And then some of it in Nevada and Utah doesn't flow anywhere. It flows into the Great Basin where it evaporates or eventually seeps into the Great Salt Lake. A lot of people backpack on the Continental Divide. I'd love to do that. That'd be so much fun. It'd take about 6 months to do it, though, so I might not be able to do it soon. But there's a long, famous Continental Divide hiking trail that goes along the length of this mountain ridge. This particular picture here is a map of different river watersheds in the US. The pink area is the Mississippi. So all those pink lines there are rivers that can link up with the Mississippi. And as you can see, Michigan, the upper and lower peninsula, do not flow into the Mississippi watershed. They have their own miniature watersheds that flow into the Great Lakes. This next picture shows where rain flows to in Michigan. So as you can see here, we're mostly in Lake Michigan watershed, but if you were to just go a little bit to the northeast, we'd be in the Lake Huron watershed, which is in green. And as you get to the southeast, you'd be in the Lake Erie watershed, and then most of the northern UP would flow into the Lake Superior watershed and the southern part into Lake Michigan. So even in Michigan, we have different watersheds flowing into different Great Lakes. So drainage basins and sediment yields. A lot of drainage basins have dust and chemicals and dirt and particles in them, and the amount of broken up material that it has caused by erosion is the sediment yield. So the Mississippi River would have a lot of sediment yield that it would deposit some of in the delta at the end of the Mississippi. And the sediment yield is basically kind of the results of erosion. Where you have erosion, it flows into different rivers, and then it's deposited in the form of sediment yield. Sometimes you'll have sediments that aren't deposited by rivers at all. Sometimes you'll have sediments that are deposited by wind. That's called loess. This here is a loess plains in China. So most of the sand and dirt you see here was deposited by the wind coming from far away, usually the Himalayan mountains. And then from there, it can work its way into different rivers. This particular picture is of an alluvial deposit in China on the edge of the Tarman Basin or the Taklama Desert. As you can see on the top right picture here, there's a large kind of yellow sandy area on the northwest part of China. That is the Taklamakan Desert. And these are rivers that are formed by mountain runoff on the outskirts of the desert that kind of flow into this basin. And then it has little rivers that create enough moisture to have agriculture. So along this basin, this very dry desert, you have lots of small towns where they take the water from the mountain runoff and use it to grow crops and so on. So this is a picture of space on one of these settlements that have rainwater coming down from the mountains. So the work of streams. Streams modify the landscape using erosion, transportation, and deposition. And they often have deltas when they meet a larger body of water like the ocean. The picture here is of the Mississippi River Delta. A Greek geographer about 2,500 years ago noticed that the shape of the Mississippi River Delta was sort of triangle shaped, so he named it Delta because it looked like the shape of the Greek alphabet Delta. I believe it's the fourth letter in the Greek alphabet. And at the very top of this, before it starts to branch out, that's called the head of the delta. And the lower part where it meets up with the larger body of water is called the foot of the delta, where a lot of the deposition and depositing of soils takes place. So streams can flood. This basically is sort of a vague term, but it usually means when a stream bursts its banks and rises beyond the usual area that it stops. And floods are sometimes measured by how likely they are to happen in a certain amount of time. So for instance, you might say a 10-year flood. So if on average, once every 10 years, a river gets up to a certain level along the outskirts of the river, you might classify that as a 10-year flood. You could have floods more frequent or less frequent than that, but that's often how they classify floods, by how likely they are to happen in a certain amount of time, 10 years, 20 years, 30 years, or so on. So you might hear 20-year flood, 30-year flood, 100-year flood. It means a flood like that is only supposed to happen roughly once every 30 years or 100 years. Seems like there have been a lot of 100-year floods lately, so they're more frequent than many people might think. This particular picture is of a river in Wisconsin that flooded in 2002. So when streams push larger sediments downriver, they have something called hydraulic action and abrasion and corrosion. Hydraulic action is water breaking up and moving rock and material down a river towards a valley floor. Abrasion is erosion caused by moving sediments. So if you have a small piece of rock kind of bouncing along the bottom of a river, and then that forces other rocks to become loose, that would be abrasion. And corrosion is minerals and rocks that are dissolved by the water. That's not as important as hydraulic action or abrasion. So this is kind of a diagram of a typical river where you have small little particles that are pushed along the river in a process called salitation. And then larger rocks are pushed along the river. They hug the river bottom, and therefore they're called traction. And then within a river, you often have fine particles that are sort of floating in the water called the suspended load. And then these things, along with dissolved water, a dissolved load, kind of make up the materials that move along a typical river. The ability for a river to move materials is called the transport capacity, and the largest particle that a river can move is called the competence. So the Mississippi River would have a larger transport capacity than a fast-moving mountain stream, but a fast-moving mountain stream would be able to move a larger boulder than the Mississippi River would, so that would have a larger competence. And the stream power is the ability of the stream to do work, meaning to reshape the landscape in the form of erosion or deposit sediment in the form of deposition or so on. So the more stream power a river has, the more change typically is occurring along the river. So here's someone measuring the deposition of the Colorado River. This particular person works for, I think, the USGS, and he's measuring the amount of sediment there is in the little Colorado River that eventually meets up with the larger Colorado River. And usually there's increased sediment as the river moves further downstream. It's had more of a chance to pick up more sediment and dirt and so on. So you often have more sediment further downriver than you would upriver. Here's another picture of the Colorado River. The base level of a river is basically the level of a river where it can't really go down anymore. The ultimate base level of a river would be the ocean, but the base level of a river in Michigan might be Lake Michigan or Lake Huron. But basically, there is a point where rivers can't really erode anymore, and then that's considered to be the base level. And on the diagram on the bottom here, where you have rain coming down and high in the mountains, that has a lot of potential energy. And then when you start having that rain move down, that's considered kinetic energy, the movement. So you can imagine if you pull back on a bow and arrow, and you pull back on an arrow and you hold it there, it has a lot of potential energy. Then when you release the arrow, that would be kinetic energy. So it works the same with water. So landscape shaped by stream erosion. This here is Victoria Falls on the Zambezi River, which is on the border of Zambia and Zimbabwe. It's 350 feet tall. It's 5,604 feet long, so it's over a mile long. So it's the largest waterfall in the world by volume of water. Angel Falls and a few others are taller, but it has more water flowing over it than any other river waterfall in the world. So factors that affect patterns of stream erosion. Climate is a major contributor to how much stream erosion you have. You often have, obviously, more erosion where you have heavier rain, where you have more mountainous areas, more elevation, and so on. So areas that don't get a lot of rain and don't change that much, don't have a lot of wind, would not have as much erosion as more dynamic regions where you have more rain and more water. Also, factors affecting patterns of stream erosion is the lithology of an area. That means what are the rocks made up of? You have lots of soft rocks, you'll have more erosion. You have harder rocks, you'll have less erosion. Quartzites is very resistant to erosion. Shale is relatively soft. Limestone is resistant in dry climates, but when it meets water, it has lots of chemical reactions and can dissolve in moist environments. So this particular cross-section shows harder rock in the darker bands and lighter rock shale in the lighter bands. And where you have harder rock, you have more sharp cliffs because of very little erosion. And where you have softer rock, you have more of a gentle slope. So other factors affecting the patterns of stream erosion is the geologic structures. Basically, these are different geological formations that can affect stream erosion, that can influence it or cause it. We'll talk about these: hogbacks, ridges and valleys, domes, faults, intrusive igneous structures, and extrusive igneous structures. So these are some examples of hogbacks and cuestas. This is a kind of a cross section of a hogback. That's where you have different layers of rock, and you have something like limestone, which is very hard, kind of pushed up at an angle, creating what looks like a little cliff. That's an example of a hogback. And then the same thing, but at a much more gentle slope, might be considered a cuesta. That's when you have strata, but it's at a much lower angle than a hogback would be. So these are an example of a hogback on the left. That is in Colorado, and a cuesta in the Crimea on the right, which is a similar thing, but at a more gentle angle. Landscapes produced by streams, erosion, ridges and valleys. This is a lot like we studied earlier in Nevada, where you had lots of valleys and lots of plains. So this is areas where you have erosion with synclines and anticlines, kind of the top of the hills and bottom of the hills, and it can produce a series of parallel ridges and valleys. This is a shade relief map of the Appalachian Mountains. And this is an actual picture of the Appalachian Mountains. Again, very pretty area. If you have a chance, check it out. Domes can also be formed by water kind of eroding lighter rock around an area that's being pushed up by underground pressure. Dome, you have uplifted strata that produces a dome, and then stream erosion that results in kind of a concentric cuestas around that. So this is a diagram of a cuesta that's sort of circular. And this is an actual one in the Sahara Desert called the Riksdag structure, or the Mauritanian Eye of the Sahara. So that's a circular cuesta. Other landscapes produced by stream erosions, faults. The diagram on the left, you have lots of different valleys that are in between lots of higher peaks. And then you have these alluvial fans that we talked about earlier. We saw the picture of in China. So you have streams and mountains that flow down into valleys that bring sediment with them. The sediment can build up and it can create the landscape you see on the bottom left there. And then faults can also be influenced or caused by stream erosion. On the right here, you have a fault scarp, and that's kind of a cliff that forms when you have a fault where one piece of rock is pushed up compared to another one. And then on the bottom, you have a significant erosion modification where just a large portion of rock is at a joint. That means you have a rock that has a break, but you don't have movement along a vertical or horizontal plane. And then in this particular diagram, it shows a large portion of rock has just eroded, leading a new fault line scarp kind of behind that. Those are relatively uncommon. This here is a fault scarp in New Zealand. So again, this is an example of that. We talked a little about that in earlier chapters. And then other things that can be produced by streams and erosions are mesas and buttes. A mesa is a large, basically pillar of hard rock on top that's eroded along the side. The hard rock on top that's erosion resistant is called a cap rock, and a butte is similar to a mesa but smaller. And then on the bottom, we have an example of intrusive igneous structure. Basically, we talked about batholiths. Those are large pools of magma underneath the Earth's crust that can sometimes push up the Earth above it and create uplift. This is an example of Granite Dome in Stone Mountain, Georgia. So this is just on the outskirts of Atlanta. They have this large mountain that's created by batholiths underneath, and it's created this unusual rock formation there. These are more examples of Colorado National Monument. These are examples of buttes and mesas here. So tectonic activity can also influence water. When you have tectonic action, you have rivers that are being, they're in mountains that are being pushed up, and that increases the potential energy. And where you have tectonic activity, that can accelerate erosion and increases potential energy. The picture here is an example of the Himalayan mountains. The Appalachian Mountains are an older mountain range, so they're more worn down, but even they have some potential energy created by their higher altitude. So there are different kind of drainage patterns where you have different styles of river that flow. If you have a circular shaped mountain, like maybe Mount Fuji in Japan, you might have a radial kind of drainage style, and that's on the right there. You can have sort of a circular drainage style. That means rivers and creeks kind of form in a circular pattern around the land in the area. You could have trellis, rectangular, or the most common dendritic kind, which is sort of like plants. It looks a little bit like the veins of a leaf. So these are different kinds of drainage styles. You have different patterns water follows when it's being drained. So we usually think of rivers kind of flowing in the valleys of an area, but sometimes you can have a river that's superimposed on an area. That's where you have a river above an area of hard rock, and then erosion slowly wears away the soft rock that the river flows in, and then it's sort of gently placed on top of a mountain range, as you see in the diagram on the left. And then you can have a river that kind of cuts through mountain ranges instead of moving along the valleys of them. It's a little unusual, but that's called a superimposed stream. And you can also have a river that stays relatively stationary while the land around it is pushed up through uplift, and that's called an ascendant stream. So an ascendant stream is a stream that remains stationary when the land around it is pushed up, kind of the opposite of an incision. So landforms of the fluvial system, we have two more units. We'll try to get to them fairly quickly. This is a picture of New Zealand, a sandbar in northern New Zealand. And so this is where sand would be deposited at the mouth of a river. Alluvial fans are sometimes formed when you have an ethereal stream. An ethereal stream is something that's temporary, not permanent. So you have heavy rainfall, you can have lots of streams that form in rivers. They can carry down sediment and then deposit the sediment at the mouth of the ethereal stream. You can have some of the sediment build up in different mountain areas. So this particular picture is an alluvial fan, the Last Chance Range in Death Valley. So this is, of course, an area that's very dry and hot, so almost any water would be ethereal and temporary. And where you have rivers, the most typical kind of a river is to have a meandering river where it kind of gently curves back and forth. And where you have these bends, you'll often have an increasing bend where, again, on the inside of the river, there's deposition and soil buildup, and on the outside, you have more erosion. And then it kind of gets curvier and curvier as time goes on. So a river that starts out as straight will usually naturally become more curvy. Occasionally, you can have a curve that kind of gets cut off from the main part of the river, and that can form an oxbow lake, which we'll see in a moment. This is an example of a curve in the river, in the Manistee River. These curves, if they're sharp, are often called oxbow curves. I went backpacking here. This is along the Manistee River on the North Country Trail. And in addition to curved rivers or meandering rivers, you can sometimes have braided rivers. These are where you have islands and sandbars that kind of form within the river itself. The picture on the bottom is the Platte River, and that's a classic example of a braided stream that's in the central plains of Nebraska. Scientists aren't entirely sure why certain rivers are more meandering and why some of them are braided. Some of them can switch between one and the other. But a braided river is, as the name implies, kind of when you have these sandbars or small little islands throughout the river. Where you have rivers, you often will have floodplains that form around them. Those are areas that are low-lying near the river, usually inside of a valley that's a little further away. And these are areas that will routinely flood. They're flat areas that usually have rich soil, so sometimes they're appealing to settlers or farmers and so on, but they can occasionally flood. And as you see on the bottom, it shows how an oxbow lake can form. As rivers curve more and more, a curve can kind of get cut off by the river and become detached from the river and form a small lake. These are oxbow lakes in England. The river just was meandering, but then the meandered bend got cut off and formed its own small little lake. So landforms of rivers and valleys, we talked a little bit about floodplains. Occasionally, you'll have an area where it can develop a natural levee. That's kind of a natural cliff that can prevent the river from flowing beyond that. So the diagram here kind of shows the creation of natural levee that can form when you have enough sand and soil kind of being deposited on the edge of a river. You can even have multiple levees where there's sort of a step formation where you have one levee, then it will drop down sharply, and then it will be flat again, then it will drop down again, and then that can lead into the floodplain. So natural levees can form along rivers that sort of contain the river, and some artificial levees are built around cities to prevent flooding. So people will often settle in these river floodplains, again, because the soil is rich and it's relatively flat. But that means you have to be very careful if you build in a floodplain that you build barriers around it to prevent it from flooding. This is a nuclear power plant on the Missouri River that flooded near Omaha, Nebraska. Thankfully, I don't think any serious damage was done. But anytime you build any large permanent structures in floodplains, there's the risk of flooding. And then we talked a little about terracing. This kind of shows about how terraces can form along the outskirts of rivers, natural cliffs that are somewhat like levees that prevent the river from flooding kind of beyond those. So these are little cliffs that can form from erosion. Deltas, we talked a little bit about these before. This is an aerial photo from space of the Mississippi River, the Nile River Delta. Cairo is at the head of the delta. That means the narrow part where it starts to widen. Cairo was actually founded in the 700s, so it's actually not a real old city compared to other cities. It's much newer than, say, Rome or Constantinople or London or Paris. And then Alexandria is a major city that is on the edge of the Nile, where it kind of meets up with the Mediterranean Sea. That was founded by Alexander the Great. It was a small town, then he founded a larger town there in around 300 BC, I think. So this is an aerial picture of the Nile Delta. And deltas can form in different formations. Where you have water flowing into a relatively calm body of water like the Mediterranean, you'll often have a wider delta. The Mississippi River has formed sort of like a bird foot shaped delta. And then the Niger River in Nigeria, where the Niger River meets up with the Atlantic Ocean, that's actually rougher. It has stronger waves that move into it. And because of that, it's a narrower delta. It's not as wide as some of the other deltas. So where the body of water is rougher, you often have smaller, more compacted deltas. The last unit, this is kind of interesting, karst landforms. Karst landforms are basically landforms that have lots of caves. That's kind of what it means. You also have lots of these cool stone pillars like you get in Vietnam and parts of China. And they're basically caused by limestone usually dissolving when it's mixed with harder rocks like dolomite or other things like that. So this particular picture is of a bay along Hang Long Bay in Vietnam. And these are pillars of rock that had softer rock around them that eroded because of chemical reactions. So karst developments, these are areas that are created through the dissolution of rock. That means sort of the disintegrating of rock because of a chemical reaction. Karst is the name of the landscape and the process that forms them. Limestone caves are an example of a karst environment. They can happen in temperate climates like Kentucky and Missouri, or in hotter tropical climates. They're not as common in colder climates because you're less likely to have the water and the chemical reactions caused by the warmth that are necessary to create them. Here's an example of an area called the limestone forests in China. And this is another example of a karst landscape. Usually it's, again, a combination of limestone and other granite, dolomite, which is harder than limestone. The limestone erodes because of chemical reactions from water, leaving the harder rock to remain there. Karsts form slower in drier climates. That's why they're less likely to happen in deserts, although they can form there. And carbonation is an important process, and that's when CO2 comes into contact with limestone and then dissolves it. We talked about that chemical reaction a little earlier. So you have these in areas where you're more likely to have significant relief, meaning different changes in elevation, although they can happen in relatively flat areas too. So this is an example of kind of a karst landscape, a cutaway where you have valleys, water kind of flows into a valley, and then there's a network of caves above the water table but below the rock that can form where the softer rock was dissolved. This is a topographic picture of a karst landscape, and you can see there are lots of little hills and depressions and valleys. It looks like it's kind of pot-marked, and contaminants can move quickly through springs in these areas. So these are areas that you have to monitor closely if there's any manufacturing or any harsh chemicals in these karst environments. Water can move very quickly in underground rivers and so on in these environments. So because of that, scientists often like to study where the water is flowing. If you have water that kind of goes underground, you want to know how long is it underground, where does it go? So they will sometimes use benign chemicals that they use to stain the water to kind of track where it ends up and how long it takes to get there, to get an idea of the speed of water that's underground or where it will start and where it will end up. So these are scientists using, hopefully, non-toxic chemicals to kind of dye the water to track where it goes. So this is another cutaway of typical karst topography. This is an underground karst environment in a temperate environment, meaning something like Kentucky or Missouri, where you have a body of water that kind of disappears underground. That's called a disappearing stream. You'll often have lots of jagged rocks and lots of depressions caused by solution depressions. Those are depressions where the rock kind of dissolves from interactions with water. And you will often have very extensive cave networks here. So where you have a place that kind of collapses, that's called a sinkhole. If you have multiple sinkholes that kind of meet up into a mega large sinkhole, that's called a uvala. And you can have some of those. So these are different landforms that you would see in a karst environment. This is Mammoth Cave in National Park in Kentucky. This is a real large underground cave network on the border of Kentucky and Missouri, and this region has lots of very large caves. A cave is considered any enclosed underground area where there's an opening large enough for a person to crawl into it. So temperate environments can have karst topographies, tropical environments can too. This is an example of vegetation along the Chinese coast. Where you have a tropical environment, you have usually more rain and faster moving chemical reactions. So erosion can happen more quickly in these kinds of environments. And karst environments in tropical climates often have very steep-sided rock formations that can form. And we saw a picture of a similar area at the beginning of this unit. And then usually karst environments are where there's some kind of relief, change in elevation in an area. But there's a karst environment called the Caribbean karst, which is common in parts of Florida where it's actually relatively flat. These areas have lots of underground caves that are actually often filled with water. And they can be very difficult for building because it's an area that's very vulnerable to sinkholes. So you can see here, this is Florida. You can see all the little lakes that looks like they're pot-marked, or it looks like a bad road in Michigan because of all the lakes that they have there. So Miami can't build a barrier to prevent water from coming into the city like they can in the Netherlands, because water can come right up from the ground that they're on. They're built on a very porous, rocky environment where water will seep up right from the bottom if there's a high tide. So Miami can't build water barriers to protect themselves like most places can. So this is an example of disappearing swallow holes. Essentially, these are sinkholes, areas where the water underneath a certain area is eroded and that causes the area to collapse. They can appear fairly suddenly. This is one that happened in Winter Park, Florida. This is a sinkhole that happened in Florida that destroyed 5 homes. So it can be a major problem, especially in areas where there's lots of urban buildup. And another interesting karst formation are called karst towers. These are fairly unusual, but those are where you have large hills kind of being pushed up and eroded at the same time, creating hills that are stacked very close together. And this particular landscape is called a classic cockpit country. And it's called a cockpit because it's like you're inside of a cockpit of a plane. It's very confined. So the valleys of this kind of environment are narrow and kind of described as cockpits. So this is an unusual karst environment called karst towers that happened in the Caribbean kind of karst environment. And of course, caves are a major part of these. We talked about that. Where you had pillars coming down, those are called stalactites. And where you have them coming up from the bottom of the floor of the cave, that's called stalagmite. You usually have a stalagmite where you have a stalactite dripping down water, and then the water kind of lands in the same spot. It has minerals, and that kind of forces it to move up a little bit. Sometimes the stalactite and stalagmite can form and meet and form a column, as you see here on the left. But it's easy to remember because just imagine the letter T. The letter T is kind of like a stalactite where you have the letter coming down, and stalagmites are kind of shaped like the letter M where they kind of pop up from the bottom. So just imagine the letter T and the letter M when thinking of stalactites or stalagmites. So finally, we talked about how in Florida, they have a Caribbean karst region that has lots of underground water-filled caves that are less common in other places. There's a great video I think I posted a little earlier about a woman scuba diving in some of these underground caves. I will post it on this unit. I think I posted it a couple units ago, but it's really interesting, so I'll make sure to repost it. But it's a TED Talk about 7 minutes long that talks about scuba diving in some of these underground caves in Florida. So it's a really fascinating TED Talk. All right, does anyone have any questions? You can send me something in the chat, or if you have a microphone, you can speak to me there. Otherwise, I hope you all have a good weekend, and thank you for joining me. Any questions? One question coming in, looks like. Oh, okay, well, if you think of anything, you can feel free to email me. Otherwise, have a good weekend. Thank you for joining me.